Hello and welcome back. In the previous lecture, we were looking at virial equation of state. We started with Gibbs free energy as a generating function to derive all the thermodynamic properties, such as this one, where the Gibbs free energy change with respect to temperature is same as the enthalpy, or it is related to enthalpy. And once we have enthalpy and Gibbs free energy, I can derive entropy, etc. And we've also expressed the residual properties in terms of the compressibility factor, temperature, and pressure. Using Gibbs free energy as the residual, as the generating function, we can express all the residual properties in terms of these quantities. And once we have done that, we have applied to a particular equation of state. Yesterday, we looked at virial equation of state. So either using 2 or 3 virial coefficients, that's the most number of virial coefficients we generally use in a process industry. We can define the compressibility factor, and we have derived the relation for the residual properties in terms of the second virial coefficient only when there are 2 terms in the virial equation of state, and tried to solve a problem based on that in the last class. Today, what we will do is try to extend this discussion for virial equation of state. What happens if I have both the second and the third virial coefficient? How do I express these residual properties? And then we'll move on to other equations of state, in particular what are known as cubic equations of state. So let's first start our discussion. Virial equation of state involving both the second and the third virial coefficients. When we have both the second and third virial coefficients, then the compressibility factor Z is, as we discussed yesterday, written in terms of 1 plus B over V plus C over V squared, right? Now contrast this with the form we had only when there is where there is only the second virial coefficient. For Z is 1 plus BP over RT, I could also write it as Z is 1 plus B over V. We chose this form because it's more convenient. When I know temperature and pressure, I can calculate the compressibility factor and hence the volume. But the moment we have both the second and third virial coefficients, as we discussed yesterday, we only tend to use this form of the expression. So we want to change this integration in terms of volume or density rather than pressure. And let us see how we do that quickly with one example first, and then we'll just generalize it and try to write the expressions for other thermodynamic properties. So my goal then is to take this equation here, GR by RT is integral 0 to PZ minus 1 dP over P, and somehow convert it in terms of volume. The way we do that is using the definition for compressibility factor. Recall that compressibility factor Z is PV over RT, which implies P is ZRT over V. So if I take a logarithm on both sides, log P will be log of ZRT minus log of V. Now I'm going to take a derivative. The left-hand side will be dP over P. The right-hand side, this is at, let's restrict it to constant temperature, so the temperature is constant, so RT is constant, it can come out, RT, then all I have left, RT dZ, or rather let's just write the whole thing out, that's easier to write without confusing ourselves. It's d of ZRT over ZRT minus d of V over V. And because temperature is constant, RT can come out, so what I have left then is dP over P is RT dZ over ZRT minus dV over V. So I can cancel these RT terms. So dP over P then turns out to be dZ over Z minus dV over V. So I can take this expression right here and put it back here in that equation for ZR over RT. Let's see what happens. GR over RT is integral 0 to P Z minus 1 dP over P, and I'm going to replace that with dZ over Z minus dV over V. right, minus dV over V. Now, limit as P goes to 0, volume will go to infinity. As pressure goes to 0, the molar volume goes to infinity, right? So, keeping that in mind, let us see what happens to this integral for GR over RT. So, what I have is GR over RT, right, is integral P going to 0, the volume going to infinity. The gas will be an ideal gas, so it will be compressibility factor goes to 1, right, Z minus 1 dZ over Z minus dV over V. The other end is at a pressure of P. The corresponding volume and compressibility factors are simply V and Z, whatever those numbers are. But at the lower pressure limit, the volume goes to infinity, it becomes an ideal gas, so compressibility factor goes to 1. Now I have to do this integration, and it turns out that this is a pretty straightforward integration. I can do integral Z going from 1 to Z, Z minus 1 dZ over Z minus integral volume going from infinity to V, Z minus 1 dV over V. I've just separated those two parts. And the first one is essentially Z minus 1 minus ln, right? So if you think about it, let's write it explicitly, maybe that will help. It is integral of 1 to Z, Z minus 1 by Z is 1 minus 1 over Z dZ, right, minus integral of infinity to V, Z minus 1 over V dV. Now, if you think about it, the first integral, it is dZ, integral of 1 to Z dZ minus integral of 1 to Z dZ over Z minus integral infinity to V, Z minus 1 by V dV. Or the first term is Z minus 1, the second term is ln Z minus ln 1 minus the integral infinity to V, right, Z minus 1 by V dV. So this is Z minus 1 minus ln Z minus integral of infinity to V, Z minus 1 by V dV. So what we have done in that sense is changed the variable that it needs to be integrated. We have changed it from P to V. Some textbooks, it's the integral is confusing in terms of infinity. If it is for some people, then it might help to think of it in terms of density rather than volume. I can write the same equation is Z minus 1 minus ln Z minus, or rather plus, integral of 0 to rho Z minus 1 d rho over rho. So this is noting that V is 1 over rho, right? So we can, when the volume goes to infinity, then the density goes to 0. And so the limits are from 0 to the density rho, Z minus 1 d rho by rho. Either of these two forms, whether I write it in volume or density, it is a little bit more helpful rather than writing in terms of pressure. So we'll take this idea forward, right? We're going to take this idea forward and write all the three expressions. Just to summarize, the following forms of residual properties are helpful. Z minus 1 ln Z integral 0 to the density Z minus 1 d rho by rho. We have obtained this simply by replacing V is 1 over rho in the previous expression for GR. We can take a derivative of this expression with respect to temperature, and we are going to end up with an equation for HR by RT turns out to be minus T integral of 0 to density dou Z dou T at constant density d rho over rho plus Z minus 1, and SR over R turns out to be ln Z minus T times integral 0 to rho dou Z over dou T at constant density d rho over rho minus integral 0 to rho Z minus 1 d rho over rho. So all the three forms of this equation, if you see, all the three equations, if you see on the right hand side, it is just the compressibility factor, densities and temperatures, derivatives and integrals of these quantities, all of which can be measured in the lab. And the left hand side, it is the residual property. So if I have a volume explicit equation of state, the right hand side can be easily obtained, and then I can use that form of expression to calculate the residual properties, right? Now, keeping this in mind, if I have now, we were talking about the virial equation of state with both the second and the third virial coefficients. This is the form we have. So the compressibility factor is going to be 1 plus B rho plus C rho squared, since we are talking in terms of densities in these expressions, right? And I can take the derivative of this at constant density, derive the expressions for GR by RT, etc., using the above relations. And what we will end up with are the following equations. Let's just write them down in a separate slide. GR over RT is going to be 2B times the density plus 3 by 2 C density squared minus ln Z, right? HR over RT is temperature B over T minus dB by dt rho plus C over T minus half dC by dt. Again, as earlier, both the second and third virial coefficients are going to be functions of temperature. We need that functionality so that I can get the derivatives dB over dt as we did yesterday, and dC over dt for the third virial coefficient. And once I have both GR and HR, it's pretty easy to obtain SR over R. It's going to be ln Z minus T times B over T plus dB dt times rho plus half C over T plus dC dt times rho squared. These are the three equations for GR, HR, and SR. Other thermodynamic quantities can be similarly obtained. Again, in both these expressions, we have the derivatives with respect to temperature for B and C, in addition to B and C itself. So once I know B, C, and their derivatives at various conditions, I should be able to calculate all the residual properties and hence changes for any process when there is three terms in the virial equation of state. Now in real life, as we have discussed yesterday, virial equation of state is applicable only if it is at low to moderate pressures and well below the critical conditions. So with that, we end the discussion for today. Thank you.